So this talk is going to be about how magnetism has repeatedly revolutionized the world and changed the way history of everything has happened. So as has already been said, I'm at the Department of Physics in Oxford, and my research group does a lot of work on magnetism, as does a number of others. And I hope in this talk you'll see why magnetism is such an amazing subject. So the first thing I'd just like to do is ask you a question. How many magnets do you own? So just think about it for a moment. Unfortunately, we're not in a lecture theatre where I could really ask you individually, but just think about that question. How many magnets do you own? Well, I suspect the answer is quite a lot. For example, you might have some magnetic letters that you have attached to your refrigerator. Lots of people have these, where you can spell out various messages, hopefully more polite than this one. But of course, you probably have a whole lot of other things. For example, you might have a microphone or some headphones, and those have magnets in them, or loudspeakers. You might have something that has a motor in it, like in your house, you might have a washing machine or a hairdryer, or there might be a lawnmower in the garden, or you may have an electric guitar. Of course, you might have a credit card. So all of those things have magnets on. The information about your credit card number is stored in a little magnetic strip. That's lots of little tiny magnets. So when you start adding it up, you probably have maybe a few tens of magnets. But then, of course, you've probably got a computer. And a computer has a hard disk in it. And in a hard disk, each of the bits of information are stored in an individual little magnet, a little grain on a hard disk. And so you can think of each of those ones and zeros stored on your hard disk as a separate magnet, in which case you haven't just got tens of magnets, you've got billions of them. So there are huge numbers of magnets that you have in your possession, I suspect, and they change the way in which we live. Now, of course, there may be a car that you have access to, get driven around in. And one interesting question is how many magnets there are in a typical car. Huge numbers. You have them in sensors, sensing something about the seatbelt, or motors that are controlling the electronic windows, or in the ignition system, or a whole range of other things. So even a car is absolutely filled with magnets. And of course, because the cars now all have computers in, there are hard disks as well with even more magnets. So magnets have completely changed the way in which our technology works. But it's an old story. So magnets were discovered a long, long time before we worked out how they worked. How were they discovered? Well, they were dug out of the ground. So it was magnetite, Fe3O4, in fact, a naturally occurring mineral that in various places in ancient Greece were discovered, that we get the name magnet from a town that is where Greek philosophy and Greek science was born. And for a long time in history, this was called a lodestone. So the lodestone was a bit of magnet you got out of the ground. And of course, you could use it for all kinds of different things. And you discover that magnetic objects would stick to a lodestone. It was a kind of magic stone. And in fact, magnets have been used by life much longer than we've been using magnets. So there are some bacteria that grow this crystal of magnetite inside them, and they actually use it for navigation. If you're a tiny little worm living under the sea, some little nematode worms have magnetite crystals inside them, and they basically travel along the magnetic field lines up or down through the sludge, where it's so dark they can't work out what's up or down, and they use magnetism to navigate. Now, a Roman poet around the years before Christ wrote a poem called On the Nature of Things. And in that poem, he speculated about the origin of magnetism. He had some rather strange ideas. So he thought about, as you can see from this little poem or extract that's written here, he had this idea that iron is attracted to a piece of lodestone due to something, little things like atoms that are pouring out of the magnet and going through space. In fact, he had this idea that when the space is emptied of these particles, that leaves a void, and that is what causes magnetic attraction. Now, this is not right. It's completely wrong. But the interesting thing was somebody like Lucretius, as long ago as more than 2,000 years ago, was thinking about the nature of magnetism and was fascinated by it. Now, what is that magnetic attraction? Well, as many of you know, what happens in magnetic attraction is you have on a magnet two poles, north and south. And the south and the north poles are attracted together, but like poles repel. So you can see those moving apart. And so all magnets seem to have a north pole and a south pole. And there's an interesting thing that can occur. You might say, well, if I can cut the middle of a magnet, maybe I can separate the north and the south pole. But in fact, you can't, because if you cut a magnet, what happens is you break it into two magnets. So there were people writing in the 1,000 years ago of cutting some kinds of snakes. If you cut the snake, a new head and tail appears on the cut parts. And in the same way, the magnet seems to be doing something similar. And so people were thinking about, what on earth is going on when you cut a magnet? So we now come to the period, I'm doing a very big sweep of the history of the world. I'm now not 2,000 years ago, but much more recently, 1543. And we have a scientific revolution. In fact, the word revolution, which these days often is used for, a revolution in a particular country where people overthrow the government, actually the word revolution originally comes from a scientific revolution. And the first scientific revolution was all about revolutions. It was Copernicus who wrote this book in 1543, just as he was about to die. And he wrote it basically trying to argue that the Earth goes round the sun, not the sun round the Earth. And so this was a scientific revolution that was all about revolutions. And there have been lots of revolutions in science. And what I'm going to try and explain in the next sort of 20 minutes or so is a lot of them are connected with magnetism. So here is an early application of magnetism. This is a Chinese spoon. It's magnetic, and it was used for divination. And so the idea was that you spun the spoon around, and which direction it fell in, it would tell you what was going to happen tomorrow if you could interpret this properly. But then what was discovered was when you spin this thing around, it often ended up pointing in the same direction. And then the realization was that, in fact, what you had here was something that was pointing north. So somewhat by accident, there was the invention of this thing. So this is the magnetic compass. This is a picture of one in 1269. The technology came from China and it came over to Europe. And this actually led to one of my first revolutions. This was the magnetic compass. And once you have a magnetic compass, you can navigate. Now, these days, we all navigate by our phones. We look on Google Maps. We use GPS satellites. But of course, for a lot of human history, we didn't have that. But what we did have was the magnetic compass. Nobody really knew why the compass pointed north, but you could use it to find your way around. And here is a map of the world. It's a pretty old map of the world. So it comes from 1569. And how was that map obtained? Well, it was essentially obtained by European people who had an access to a magnetic compass who could then navigate the world. And so they did, and they made maps. So we actually understood something about the structure of the world. If you know your geography, you'll probably see that this map isn't quite right in a number of details, but it's not bad for 1569. And of course, what this also led to was colonialization. So lots of European nations ended up taking over many other countries in the world. That's why, of course, if you go to South America, a lot of people speak Spanish or Portuguese. If you go to the United States, they speak English. And so European nations colonized the world. That had a lot of bad things associated with it, some good things, but our history is essentially determined by this scientific discovery. The discovery of the magnetic compass was in some sense morally neutral, and then it's a question of what people did with it. But it certainly changed the world. Now, there are lots of other applications of magnetism, so I'm going to go a little bit further forward now to one of my scientific heroes. So this is William Gilbert. He's not as famous as he ought to be. So he was living in a time when the things I've got written on the left were some of the applications of magnetism that you could find in books. So what could magnets do? Well, they could do things like they could bestow eloquence. They could make you better at talking. They could cure feet pains, or they could do various things to do with your bowels. As you can see, there's a lot about the bowels in that list. They could keep you youthful. They could do some marriage guidance, and even very specific things. I like the one at the bottom of this list: picks up gold from the bottom of the deepest well if first preserved in the salt of the suckling fish. So there were all these kind of crazy things that were going on. And what you would also find in books are some other scientific principles, which are that lodestones, that is magnets, they don't work in the presence of garlic or in the presence of diamonds, and also magnets only work in the daytime. Now, you can probably think of some scientific experiments you could do even this evening if you have some garlic in the house, or if your parents might lend you a diamond ring, or if you do it at darkness. You can probably show that these are false. Magnets do work in the presence of garlic. They do work in the presence of diamonds, and they don't only just work during the day. But you'd find these things written in books. And William Gilbert basically spent a lot of time testing all of these things. I'm not sure how he tested them all, but he tested a large number of them, and of course found that they were rubbish. And he wrote a book about it called De Magnete. He wrote it in 1601, and it was a huge bestseller. And it's actually quite amusing to read, because he is very rude about the other scientists. Thus do pretenders to science vainly and preposterously seek for remedies, ignorant of the true causes of things. There was a big speculation about why the compass works, and some people thought, well, the compass is pointing towards the North Star, Polaris. You often see it north from here, and on a clear night. And one of the ideas was that the North Star, the pole star, was magnetic. And this was said by one Lucas Agaricus, and Gilbert is very rude about him. And with a veil of mathematical erudition does he cover many similar disgraceful stupidities. So it's a very amusing book. But essentially what he did was he did some experiments. And one of his experiments, which was a very clever thing to do, here's his picture of it. Here's my picture of it, which is a little bit flashier because I've got an access to computers. But essentially what he did was he made a magnetic sphere. He got lodestone, he got magnetite, and he made a sphere out of it. And then he got a compass, and he moved the compass around the magnetic sphere. And what he realized was that the field lines from the sphere went around in this pattern that I've shown here. And he called this a terrella, which means a little earth. And what he was basically demonstrating was that if the spherical earth was magnetic, that would produce a magnetic field around the earth that varied as you went around the earth. And there were experiments. People had gone off on ships and shown how the compass direction changed as you went around the earth, and how the angle of the magnetic field with respect to the ground would change. And he showed that there was very good agreement. And because of this little model that he'd made, he said, well, okay, it's not the North Star. It's not a mountain somewhere north of here, which was another idea people had. Maybe there's a magic magnetic mountain north of here, and that's why the compass points north. No, he said, it's actually due to the Earth itself being magnetic. Now, he thought the Earth was made of lodestone, and that's not quite right. But he was on the right track. And the key thing was that he was doing experiments. And so really this is a crucial thing that he did. I've got some more quotes from him here. I won't go through it all. He rubbished magnetic perpetual motion machines. Some people thought certain metals agreed with certain planets. And he said, what on earth is in common between Mars and iron, except that, you can implement swords and artillery out of iron, and Mars is supposedly the god of war. What connection do these things have? This is rubbish, just created by simpletons and raving astrologers. Okay, so he wasn't the most polite of people, but he was trying to find the truth by using experiments. And that really is the second revolution that magnetism gave, because he was really the first one to do proper experimental science, which is now absolutely standard. How do we know that certain scientific ideas are right or wrong? We do experiments, and that's really important. Okay, and in fact, even at the time, Ben Jonson, who was one of the contemporaries of Shakespeare, he was so impressed by Gilbert, he wrote a play called The Magnetic Lady. And it's a play in which all the characters are named after bits of the magnet. So you can see there's Lady Lodestone and Mistress Keeper, keeper is the thing that goes on the end of the magnet, and Captain Ironside, and all of this kind of thing. And so the whole play is all about things to do with magnetism. Anyway, probably many of you are not so interested in Shakespeare and Ben Jonson and more interested in science. So I'll get back to that. Now, after this time, there were many other people who followed Gilbert's lead, and they did experiments on magnetism. One of them was Hans Christian Ersted, a Danish scientist, and another one was André Marie Ampère. And I'm going through this very quickly, so I will just cut to the chase and say essentially what came from their work was a realization that if you have an electric current carried by a wire, that will produce a magnetic field. And this could be detected by a compass needle, and it would produce forces and all of that kind of thing that many of you are learning about in your physics lessons. So this was a crucial idea, because up until this point, if you wanted a magnet, you had to dig one out of the ground. But now you had one that was turn off and onable, an artificial magnet. So you could put a current in, you could have a switch, you could turn the magnet on or off. Now that's something you can't do with a permanent magnet. It's always switched on. There's nothing you can do. But now you had artificial magnets. So just compare the one on the right, which is always on, to the one on the left. So now you can have an electromagnet, a magnet that you can turn off and on. And that led to all kinds of exciting things. One of the things it came through, we're now going into the 19th century, through Michael Faraday, who worked at the Royal Institution in London. And the thing he discovered, well, he discovered lots of things. He took pictures of magnets, essentially by putting iron filings. In fact, this is a drawing he made just a little bit before a lot of the photography started. Here's another drawing from Faraday. I tried to recreate his experiment using iron filings in my garage. So this is my version of it. But of course, you've probably done this kind of experiment. Look at the patterns of lines around a magnet. So he did that. But then the other key thing that he did was that he invented the motor. Because what he realized, and this is a schematic I've drawn of his experiment. He had a battery, he had a beaker full of mercury, which conducts electricity, and then he had a permanent magnet. That's the sort of gold thing you can see in the center of the, I'll see if I can move my mouse and show it to you. Yeah, so this is a permanent magnet. And then he had a metal bar that was hung by a pivot, creating the circuit. So he passes a current through here. So you now get a current going through this essentially rod. It's just seeing a magnetic field. And what happens is, and I'm afraid I haven't animated this, but it basically starts stirring around in the mercury. So what he'd done is he'd used his electric current to produce motion. And so essentially what he'd done is he invented something a little bit like a motor. And of course, what that has led to is motors and generators, wind turbines, and essentially all of the infrastructure that we have with our power station. The fact that you can have electricity in your own home is all, and in fact, the fact that we can build modern cities which are all connected together by wires is essentially due to this revolution of Faraday's. And this ability to turn motion into electricity and then electricity back into motion. So generators and motors. So it's created the modern world. Okay, there are a number of other things. I'm going to go into the 20th century here, and I'm going to go through some things quite quickly. So, well, back in the 19th century, James Clerk Maxwell explained that magnetism was important in light, because essentially light is an electromagnetic wave. And those of you, I know some of you are doing A-level physics, so those of you who are doing A-level physics may have come across this expression, which is the speed of light is related to some factors that are to do with electricity and magnetism. So there's an equation, but the picture also shows you an electromagnetic wave, electricity and magnetism propagating off each other. And in fact, this person, who you may recognize, this is one Albert Einstein, he was very worried about Maxwell's equations, because Maxwell had said, this is the speed of light, but the speed with respect to what? And this so worried Albert Einstein that he invented relativity, which tried to explain this puzzle. And one of the consequences of relativity, and now this, I'm going to show you a horrible equation. This is something that you will do when you do your degree. This is a frightening equation, but it's showing that magnetism is fully relativistic. And the only thing you have to notice from this equation is that there is a matrix, which is a 4x4 matrix. And it's 4x4 because there are 3 dimensions of space and 1 of time. And Maxwell's theory is a theory of space-time. It's a 4-dimensional theory. So when you come and do a physics degree, you'll learn all about this. But it comes out of Einstein's theory. He's realizing how to do magnetism and electricity unified in space-time, and he saved Maxwell's equation. So that's my 5th revolution. My 6th revolution comes from these 2 people. So the one on the left is Niels Bohr, who did a lot of inventing of quantum mechanics. And the one on the right is Hendrik Van Leeuwen, who is a Dutch scientist. And they both came up with the same idea, and they published it independently. So they came up with a theorem, which is called the Bohr Van Leeuwen theorem. And what that basically says is that magnetism is impossible. Now that's a bit of a worry because we've seen that magnetism actually happens. So how do we get out of this? Well, their theorem assumed that classical physics was correct. And so basically what they had shown was that if you've seen a magnet picking up iron filings, you've already realized that classical physics is not correct and you need quantum mechanics. That puzzle is only shown to be correct by quantum mechanics. And here are some other scientists, don't worry about the equations, but the people shown there are Heisenberg, you may have heard of his uncertainty principle, and the person smoking the pipe is Wolfgang Pauli. And these 2 people were very, very important in developing quantum mechanics and developing the quantum mechanics of magnetism. Now, another big discovery that was very, very important in magnetism was the discovery and the invention of magnetic information. The fact that you could store information using magnetism. And some of the earliest ones were done by this chap, Oberlin Smith, and essentially had an idea of having magnetic particles on a wire that spooled around. There were various other versions of it. This is one by a chap in 1898, where you store magnetic information on a cylinder. Basically, you rotate the cylinder around and you write magnetic bits onto the cylinder. So there are a number of these things that were tried, here is a sort of slightly more modern but still incredibly antiquated version. This is the magnetic tape. And actually still to this day, if you want your information to be stored for decades, the most reliable way of doing it is using magnetic tape, even though none of us really see magnetic tape in our daily lives. Actually, if you really want some bit of information to last for 50 or 100 years, the most reliable thing is magnetic tape. And so for a lot of the 20th century, a lot of information was stored on these kind of magnetic tape machines. And of course, the modern version of this is using a magnetic hard disk, which is what we have in many of our computers. So this was a huge revolution because what it meant was that no longer did you need to write things down in books. You could store them in computers. And here is an example. This graph shows you how much information could be stored in a square millimeter as a function of the number of years. So you can see around 1960, 60 years ago, you could store a few bits on a square millimeter. Now we can store something of the order of 1 billion bits on a square millimeter. So all of our hard disks have been able to store more and more information, which means not only text files, but audio files and image files and video files, which take even more information. And another revolution has been in medicine. So we've worked out how to use magnetism to do imaging. So this is a picture of a human brain taking slices through. And before the invention of magnetic resonance imaging, if you wanted to take slices of a body, you'd have to use a meat cleaver, which is obviously not very good for the patient. So the great thing about magnetic resonance imaging is it's completely non-invasive. So you can go into one of these machines and you can have slices analyzed of you, but you don't feel a thing, and it's perfectly safe. And why is it perfectly safe? Well, essentially, what the principle is that you are mostly made of water. And water is H2O, 2 hydrogens and 1 oxygen. And the hydrogens basically contain a proton in their nucleus. And what they do is they stick the patient in a magnetic field. So they use a big magnet. And then the protons will basically start their magnetic moments, because protons are little magnets. They will start processing in the magnetic field. And the wonderful thing is you can use various other details to do with the environment of the protons and some clever electronics to then work out these slices. But it all rests on the fact that a proton is a little magnetic moment and a magnet, and you also put that inside a big magnet. So here is a picture of a magnetic resonance imaging machine. Some of you may have even been in one. So what's the next revolution? I've given lots of historical revolutions. What are the things coming up in the future? Well, the future is always hard to predict, so I'll just say a few possible things that are very important in research, and then I'll finish up with a list, and then I'll take questions. So one exciting area of current research is magnetic molecules, and they're all rather pretty. So here are some pictures of magnetic molecules. Up until now, we've been dealing with magnetic atoms or magnetic crystals, but we've started to work now a lot on magnetic molecules. These are made by clever chemists, and these particular molecules, I haven't got all the atoms shown, but you can see some of their structures. They have particular values of spin. This is something known as the spin quantum number, and it tells you how magnetic they are. And you can see the one in the bottom left-hand corner has a spin value of 83 divided by 2. And that's really pretty big, because often we are dealing with, for example, a proton, and a proton or an electron has a value of this quantity of 1/2. And this molecule has 83 over 2, so it's very big. Now, why are these interesting? Well, they're interesting because we want to try and work out the boundary between classical and quantum mechanics. And so if you take a permanent magnet, for example, one that you might buy in a shop or have in a device, that has a very, very large number of atoms in. So in fact, the spin quantum number might be of the order of 10 to the 20. That means 1 with 20 zeros. On the other hand, an atom might have a spin which is about 1. But these magnetic molecules are, which you might call magnetic clusters. They're larger than atoms, but they're obviously smaller than particles that you can make or nanoparticles. And so people studying magnetism are looking right the way from atoms to these huge permanent magnets and trying to discover when you move from the quantum to the classical and how that works. Okay, one other thing that is very exciting at the moment is looking for magnetic monopoles. Now, I'm not going to say too much about this idea. We have found that magnetic monopoles exist as stable species inside certain crystals. And very recently, I've been involved with a project where we've been trying to measure these and look at them with a very sensitive squid magnetometer, and also by simulating them in computer programs. And one of the things that we've tried to do is to see if we can measure the noise signal from the magnetic monopoles that fluctuate around inside the crystal. And here is some data that we've got. Now, this data here is when we are actually measuring an empty coil, so there's no signal. And the great thing about this is I can actually play it. So I will play the signal. And let's see. So this is the background with no, and now we put the sample in, and you can hear there's a lot more noise. Now I've taken the sample out, so there's no noise. And then we'll put the sample back in, and it becomes very loud. So we've tried to see the sound of magnetic monopoles, and so you can hear what they sound like. They sound like hissing things, but that's because there's a large number of them fluctuating around. So, what are the next revolutions? Well, there are a number of things we can possibly have. We can look at what we call quantum magnets, and this is a big area of research, trying to understand how quantum mechanics and magnetism work together. We also study things called frustrated magnets, And this is essentially where you put magnets together in a way that they really don't like. We frustrate them and we put them into a crystal lattice where they really can't get into a comfortable position. And it turns out when you do that, all kinds of exciting things happen. We look at various things we call emergent excitations. And there's a basic principle here that when you take an interesting material and you have lots of complicated interactions, new things occur. And we call this emergent. And one of them is this thing called magnetic monopoles, where essentially we've tried to separate the north and the south poles of magnets inside materials. There's also a lot of research going on in spintronics. Now, spintronics is a fancy word, which is basically making the point that ordinary electronics are dealing with the charge of an electron. Spintronics is dealing with the spin of an electron. And dealing with those spins and trying to make new devices is the goal of spintronics. We're also looking at the way in which electricity and magnetism could interact in new ways, and that is the subject of multiferroics. And we're also looking at superconductivity, because it turns out that magnetism and superconductivity are really closely connected, but that's the subject of another talk. And also, as was mentioned right at the beginning, we've been looking a lot at what we call quantum materials, that is crystals in which the quantum properties become really important. And so, in fact, the research groups that we have in the Department of Physics, they are all known as the quantum materials groups, and they are all working on aspects of this problem. And also, we're trying to understand a very new development, which is the interaction between magnetism and topology, which is all to do with the shapes of things. And it turns out that properties associated with the microscopic nature of the materials have various topological signatures that have very important implications for properties. So there's a lot of things going on, but I hope in this talk I've managed to convince you that magnetism has, throughout human history, repeatedly revolutionized the world, and I think it's going to carry on doing that. So thank you very much for listening.
Thank you so much, Steve. That was such an interesting talk, and I love the idea of science revolutions. That's just a brilliant way of putting it. So yeah, if anyone has any questions, pop them in. So there's a Q&A function at the bottom. I've noticed some people putting it in the chat. That's fine, but we've got more chance of seeing it if you pop it in the Q&A. So get popping in your questions about anything to do with the talk or magnetism in general, what Stephen's research is. I'm sure you can talk more about that if people ask, anything at all, because yeah, that was really interesting. Such a fascinating history as well behind magnetism, loads of people involved and so much we don't know as well. So that's great. So what have we got coming through?
Okay, I've got the Q&A. I can see it here. So
you can see them as well. Yeah. Do you want to pick something to answer?
Okay, well, they're coming through thick and fast now. So I'll take the second one on the list first. What exactly is a squid magnetometer? So we have one. In fact, we have one in the Department of Physics. A squid magnetometer. Squid is a short name for superconducting quantum interference device. And it uses this property of superconductivity as a very, very sensitive sensor of magnetism. So we use a squid magnetometer to measure magnetic materials. Oh yeah, so someone has also said, I'm doing these in the wrong order, can you make magnetic paper? Yes, you can. And in fact, the early development of magnetic tape was exactly that. In fact, there was an accidental discovery to do with cigarette paper. So the old-fashioned cigarettes, I think this is before the Second World War, had a little gold band around them, and they had a machine for putting the gold band on the paper. And actually then they realized that that same machine could be used for putting a magnetic coating on the paper. And it's actually how they invented one of the magnetic tapes. I think BASF tapes were invented that way, somewhat by accident. I've missed off the first one, which is asked about electroweak theory. That's a very complicated question. And the answer briefly is that magnetism doesn't directly relate to that, because the first thing you unify is electricity and magnetism. And then there's a more complicated theory that unifies that unified electromagnetism with the electroweak theory. So it's a sort of separate thing, very complicated question. What exactly is electron spin and why is it so significant in science? So the electrons, like protons and in fact like neutrons, they're all little magnets. And so the fact that the electron has a spin turns out to be really, really useful in, for example, there's a diagnostic technique called electron spin resonance, which is really important in chemistry, really important in biology. And so it's used in all kinds of biological and medical applications. But it's really important for us in physics too, because the fact that the electron has a spin also determines the magnetic properties of materials. So why is iron magnetic? It's because it's got lots of electrons in it. What new technologies might we see in the near future as a result of magnetism research? It's always hard to say, I think, what new technologies are going to appear. And that's because for a technology to be applicable, two things need to happen. First of all, it needs to work, but then secondly, it needs to be cheap. And so quite often, technologies are invented that never make it to the marketplace because they're just not economic to replace something we already have. So it's really hard to predict. But I think one thing that we're facing is, you may remember that there was a graph I showed of the number of magnetic bits that you can store on a particular area. And actually that's starting to plateau. And it's because we're really finding big engineering challenges with getting more and more information onto a hard disk. And so I think new technologies are going to have to appear. They'll probably be magnetic technologies. They may take a bit of a while to come through, but I think these magnetic molecules have got quite a lot of promise. So it may be storing more information in a smaller place, but it's really hard to predict. Do magnets lose their strength over time? The answer is yes, they do. And in fact, this is one of the big worries people have with storing magnetism in smaller and smaller areas, because in fact, one problem is that just the thermal fluctuations can cause magnetic bits to flip. So, for example, one way in which magnetic information can be stored for a very long time is actually in geomagnetism. So the Earth's magnetic field points at the moment from north to south, but after a few 100,000 years, it reverses. And the reason we know this is because all of that information has been stored in rocks. And so that information does seem to last for millions of years, but it's because it's stored in a great big rock. When you have smaller magnetic bits, they can fluctuate more quickly. So yes, magnets can really lose strength over time. But if they're big enough, they'll keep the information. Are magnetic monopoles unstable, and what destabilizes them? So pure magnetic monopoles are not supposed to exist in nature, and lots of people have spent a long time looking for them and have not found them. The ones that we've found in crystals, they're almost kind of cheat monopoles. So we haven't really violated any laws of physics. What we've done is we've found what are called emergent particles. They're things that behave very much like magnetic monopoles, but they're just made up of magnetic spins underlying them. They are unstable if they meet a magnetic monopole of the opposite charge. So the magnetic monopoles have two different magnetic charges. They could be plus or minus, and we create them in pairs. So we make a plus and a minus, and they can wander off. But if a plus meets another minus, then it will be annihilated. What shall I do next? What is a magnetar? So yeah, a magnetar is a particular type of neutron star. So the biggest magnets we know of in nature, and the ones that create the largest magnetic fields, are in neutron stars. And magnetars are particular types of neutron star, essentially. And they're very, very magnetic. How do bees rely on magnetism for migration? Don't know precisely with bees, but lots of animals do rely on magnetism for migration. Lots of animals rely on a variety of cues, like we all do. You might smell something, it must be dinner, I walk downstairs, but I'm also using my eyes, and I'm also using my ears to listen to various sounds like a door opening or whatever. And similarly, lots of animals work on a number of different cues. But bird migration, for example, is very important. Many birds do seem to use magnetism for migration, but it's still an unsolved problem of exactly why they do it. There are a couple of rival theories. One is that there's magnetite in the beak of the bird, and the other one is that they essentially have a compound in the back of their eye, which there's a particular chemical reaction that's influenced by magnetic fields, which involves free radicals. And so it's thought, if this mechanism is correct, and it's the one I must admit I think is more likely, then it may even be that birds can see magnetism, because it's hardwired into the chemicals in their retina. So they can kind of look over there and go, oh, it looks a bit north over there. And that's how they navigate. But they also use other cues as well, and they use light. And how much longer do you want me to carry on for, Helena? I don't want to.
Oh, I'm sure you could keep going for ages. Another 10 minutes or so. I think 10 minutes.
Okay, fine. I'll try and make sure that I will answer all the questions. I'll try and go to the top of the list. Can a magnet be broken down and crushed and still work, or would it lose its power? Well, if you do beat magnets up a bit, you can, depending on the magnetic material, some of them are very robust. Some of them do actually lose their magnetism from a certain amount of knocking around. And it's because one of the things that can happen inside a magnet is it can break up into a series of domains. And I saw some of these sketched rather beautifully in some of the posters. And some materials, the domains, really very difficult to make them to form, but in some cases, just even bashing the magnet can cause the domains to move. What are the potential challenges of building and creating quantum computers? Oh, it's a big question, but as a brief answer, one of the problems is that you have to create a quantum system that is not interacting with its environment because you want it to be able to evolve coherently and purely. But at the same time, you want to be able to read out the answer and input the answer, so you have to interact with it. So this is the problem. You've got a system that you mustn't interact with, that you've got to interact with to get the data in and out. So that's my brief answer of where the big problem is. Could magnetic monopoles be found elsewhere in nature? Well, our approach in Oxford and a number of other groups is looking at them in certain types of crystals, and we've found them in certain types of crystals, and we are beginning to understand that more and more. A number of physicists have also spent probably more than 30 years looking for them at the bottom of particle accelerator, bottom of mines using sensitive detectors, and they've not found them yet. So they may exist in the universe, but just be very rare. But research is one of those things that you just have to keep trying things, and maybe somebody listening to this webinar will find them. How does the spin change in the magnetic molecules? Well, it's all to do with the way in which the magnetic moments are lining up. And so essentially what happens is some very clever chemistry people design these molecules, and they try and do it in such a way that they can get various magnetic atoms to talk to each other in particular ways. And there's a bit of luck in it, but there's also quite a lot of science as well in governing the design of this. Can you make anything from magnetism that you use in your daily life? Well, if you heard the start of the talk, in our daily life is filled with magnetism. So yeah, we're using magnetism right now. I mean, this microphone that I'm using that's picking up my voice has a magnet in it. So we're already using it. What do the magnetic flux lines look like on a magnetic monopole? Well, that's a really good question. It's exactly the same as an electric charge. So in nature, you normally don't have magnetic monopoles, as I was explaining. You have dipoles, a plus and a minus. But what you have with the magnetic monopole is just a plus or just a minus. And so the magnetic field lines away from a monopole look exactly as you would have from the electric field lines from a positive or a negative charge. How deep would you have to go down to the Earth to find magnets? Well, if you're in the right place on the Earth, they're there on the surface. So there are various magnetic rocks that the Greeks just picked up. But there's a lot of iron as you go further down in the Earth, and a lot of iron is magnetic. Although we actually think that the magnetism of the Earth is not primarily due to the iron. It's due to the fact that the Earth's core is molten, and you've got currents of molten liquid moving around in the liquid core and creating a thing called a dynamo, and that's what produces the magnetic field of the Earth. With regards to electromagnetism, specifically the motor effect and the generator effect, can electricity produced by the generator effect be used to cause movement via the motor effect? Yes, yes it can. You lose a bit of energy in the process though, because nothing's perfectly efficient. And this movement then powers the generator effect again in order to create an infinite loop of electricity generation. Well, that's the problem. Every time you do this, you lose a bit of energy. So I'm afraid with perpetual motion machines, it's not going to work. But good try, plenty of people before you, but no one succeeded in doing it, and for a good reason. You can't get something for nothing. What's the strongest magnet we can conceive of? Well, I think the strongest magnet is the magnetar, or the neutron star that was mentioned earlier. But on Earth, the best material we found is a thing called neodymium iron boride. And if you see one of those super strong magnets that they sometimes have in demonstrations, I'm sure Helena uses them, those are made of this neodymium iron boride. But one of the big scientific challenges is to try and find a material to replace that, because it's very environmentally unfriendly to mine neodymium. And the problem is we've got them in all our wind turbines and in lots of other things. So we really need to replace that. So that's a job for one of you. When will the Earth's magnetic poles change again, and will it impact the magnets we use? Well, it's likely the Earth's magnetic field will change again. I think we've been in the current state for about 500,000 years, or is it 700,000 years? I can't quite remember. In my little book, a very short introduction to magnetism, there's a graph which shows you all of this. And we've actually been in a stable situation for much longer than you normally should do if you look at the history of it. So we really are due for another change. But whether it will happen in 100 years' time or a few 100,000 years' time, we don't know. So that's something that's it's not going to happen soon anyway. And one of the things we're not entirely sure of is how long the process of change is, whether it happens over 10 years or 100 years or something like that. And also, what do birds do when that happens? Who knows? So there are some really interesting questions. What's the difference between space's magnet and the magnets we use? Well, out in space, there are magnetic fields. So close to the Earth, it's the Earth's magnetic field, and a number of other planets in the solar system have magnetic fields. The sun has a magnetic field. If you go further out in space, there's much weaker magnetic fields, and coming from all kinds of different things, charged ionized gas and things like that. So you get a huge range of magnetic fields in space. Generally in space, it's a lot weaker than it is on Earth, because you need something like a planet or a star to produce a magnetic field. And if you're out in the middle of nowhere in deep space, the magnetic field is relatively small. How does magnetism affect topology? This is rather a complicated area and a bit difficult to explain, but essentially the electrons inside a material have certain topological properties. And this is to do with the fact that electrons are waves, and the waves have certain topological properties that depend on the material that you're in. And that is important for the magnetic properties too. But that's maybe the simplest answer I can give to that one. If you make a very big magnet, would it have a bigger magnetic field? Well, up to a point. And there are very big magnets, for example, in CERN, where they accelerate particles around the ring for the Large Hadron Collider. But generally what happens is when you make a magnet bigger, you just make the region in which it has a large magnetic field bigger. So for an MRI machine for a mouse that they have in a zoological lab, and an MRI machine in a hospital where they want to put a patient in, a human patient, you need a bigger magnet. And it's not because of the bigger field, it's just because you want a bigger volume for the magnetic field in there. Right. What happens with frustrated magnets, meaning what effects do they create? Could you use it to store information? Yeah, there are people working on that to try and store information in various frustrated arrays, usually made artificially. Yes, there are magnetic particles in certain magnetic organisms. There are so-called magnetotactic bacteria that have magnetic particles in, and there are these little nematode worms. And in fact, in lots of birds, there's magnetite in the beaks, and there was a theory that this was connected with magnetic navigation. And yes, other planets contain magnetism as well. So not all of them. I think Jupiter has a reasonably large magnetic field, if I remember correctly. Not all of the planets do. Generally, if they have a molten core that has solidified, they lose their magnetism.
I think maybe just a couple more questions.
I'll do a couple more.
So if you want to scroll through and see if there are any really good ones.
Yeah, magnetism finishes at the Curie point, and at absolute zero, magnets become their most magnetic. Yeah. So, and do they have any? Maybe I'll finish. Do they have any health benefits? We don't think so. In particular, there are things you can buy magnetism for your health, but don't believe any of it. But it's good for your brain. So I think if you read about magnetism and you think about magnetism, it's such an exciting subject. You just feel better, and that has to be good for you. So I'll stop there.
Brilliant way to finish. Yeah, so read all about magnetism and it'll be good for your health. That's the take home. Brilliant. Thank you so much for that. And thank you all for your fantastic questions. So if we give a virtual round of applause, I guess, to Stephen. Thank you very much for your talk there. And I hope you all found that really interesting. I know I did.